Okay, good evening, ladies and gentlemen. This is Professor David J. De Los Reyes. What date is today? 25. The date for today is May 25, 2024, and the time is around 10:08 p.m. Okay, my subject matter for this evening will be a long video format, and this is a continuation of my long video format topic, DC circuit. The topic for tonight will be a very interesting one because the concepts we will be discussing tonight is actually the one of the most important thing in the so-called study of DC circuit. That is, in the so-called computation of a current on a certain portion of the circuit by using advanced solutions. Okay? For the previous discussions, we've done already the series parallel concepts on how to compute current on a certain part of the circuit. But for tonight, we will be discussing one of the advanced solutions, and that is actually the so-called, that is in the computation of the current. It will be by using the so-called Kirchoff's current law and Kirchoff's voltage law. Okay? And this will be applied to, for the meantime, we are just considering a circuit in which the voltage source is just one. Because if the voltage source is more than one, that's another story. So for tonight, we will be discussing the solution of a current on a certain part of the circuit using Kirchhoff's current law and voltage law, considering for the meantime, one voltage source. Okay, let's proceed. The title of the subject matter for tonight will be DC circuit, and this is now lesson number 8. We are running smooth no matter what happens in this world, okay? And the title of the topic will be Kirchhoff's current and voltage law in the so-called computation of current on a certain part of the circuit in which the voltage source is just only one. Okay, for the meantime, we are just considering voltage source to be equal to one only. Okay, let's try to bring out the formulas needed. Kirchhoff's current and voltage law. Kirchhoff is actually the family name of an engineer who invented this so-called concept of Kirchhoff's current and voltage law. This is a family name, right? Just to summarize it, I am an electrical engineer, so I will just give you the summary of this Kirchhoff's current and voltage law. The number one concept or formula that we will be using will be the so-called Kirchhoff's current law. I place it here, current entering equal to current leaving. Meaning to say, if we are given a junction here, the current entering this one will be I1. Okay? And the current leaving might be I2. Or there could be another third current going out. We call that equal to I3. Considering again this junction, there might be current going in this direction, and we call that I sub 4. Right? This is now just a summary. The meaning of this, current entering equal to current leaving, meaning I sub 1 should be equal to the current leaving is the current leaving this junction is I2, I3, and I4. So by using Kirchhoff's current law, I sub 1 should be equal to I sub 2 plus I sub 3 equal, plus I sub 4. That's the meaning of this. Okay? It's very easy to understand, right? At any junction, current entering should be equal to the current leaving. The current entering is I1. The current leaving is I2, I3, and I4. So if we try to bring out Kirchhoff's current law, I1 should be equal to I2 plus I3 plus I4. Just considering this example here. Okay? That's a very general thing, right? So there are 5 currents leaving a junction, there should be 5 currents on the right. If there are 6 currents, there should be 6 current. Okay? Or that's the so-called Kirchoff's current law. The considering a node or junction. Okay? Uh, Kirchoff's voltage law. Kirchoff's voltage law. The summation of voltages should be equal to 0 considering any closed loop. Okay? The meaning of this, the summation of voltages and they should be equal to 0. Okay? Voltage source will be a plus and voltage drop should have a negative sign. In taking the summation of the voltages, considering Kirchhoff's voltage law, summation of the voltages, all voltages that are considered to be voltage source should have a positive sign. And all voltage thing that is to be considered voltage drop, the sign should be negative. And the summation of a plus and minus on the left hand side should be equal to 0. It's easy to, what you call this, simplify this one. Kirchhoff's current and voltage law. Kirchhoff's current law, current entering equal to current leaving, same as this one. And Kirchhoff's voltage law and any closed loop, right? The summation of the voltages should be equal to 0. Voltage source should be plus and voltage drop should be considered a minus. And the right hand side should be equal to 0. Okay? So there are only 2 formulas on the so-called study of DC circuit lesson number 8, that is Kirchhoff's current and voltage law. That is current entering equal to current leaving, and the summation of the voltage should be equal to 0. To better understand the concept of Kirchhoff's current and voltage law, I will try to bring out an example problem. The voltage source for the meantime is just only 1, because if the voltage source is 2, that will be another story. Okay? So to simplify the concept on how to emphasize Kirchhoff's current and voltage law, we will just consider for the meantime 1 voltage source. So in here, I got a DC circuit. This is a DC. And I got how many resistances? This is 1, 2, 3, 4, 5, 6. There are 6 resistances, okay, connected to this voltage source, which is 12 volts. It is DC. And the orientation of the resistances are actually a combination of series parallel. Anyway, we are done with the concept on how to, attack a series parallel circuit. So we know that one. So prior to going to this, okay, we finish first the series parallel concept. Okay, so these are the given values. 1 ohm, 2 ohm, 3 ohms, 4 ohms, this 5 ohms, 6 ohms. The one at the middle is 3 ohms. Okay? And the problem is just asking what will be the requirement there. Sorry for that one. We are asked to find, I forgot, find I sub 3 ohms equal to. The current, the problem is asking what will be the magnitude of the current passing through this 3 ohms load, okay, by using Kirchhoff's current and voltage law. Okay, because actually we could present so many solutions here, but for the meantime, we are discussing Kirchhoff's voltage and current law. So if we try to compute for the current here, we will be using Kirchhoff's current and voltage law. Okay, let's proceed with the solution. Consider junction N. I designate this junction here or node to be N. And I place the designation of the current. Okay, let's go back to the circuit. The total current emanating from the 12 volt source is just designated capital letter I with the subscript T. Current going out here on the, this is a junction, right? I designate the current going here to be I sub 2. And the current passing through the 3 ohm load, I designate that as, for the meantime, I place it as I sub 1. But for I sub 2, there are some easy things for I sub 2, because if this is I sub 2, the current passing here should also be I sub 2, and the current passing here should also be ISO 2. So for these three resistances, the current are actually the same and it is designated as ISO 2. That's very important because when we take the summation of the voltages, okay, we should take note of the current passing through each resistance. Okay, let's try to bring out the solution. Considering junction N and using Kirchoff's current law, current entering equal to current leaving. So meaning to say the current entering this junction here is I total, and the current leaving is actually I sub 1 and I sub 2. So I place it here. I total should be equal to I sub 1 plus I sub 2. This is actually Kirchoff's current law. Okay? Considering any junction, current entering should be equal to current leaving. So actually, we got three unknowns: I total, I sub 1, and I sub 2. For the meantime, we got three problems. Okay, but don't worry, we will be bringing out another two equations to eliminate the other one, so we could solve simultaneously the unknowns. Okay, first loop. Considering the first loop, we will be using Kirchoff's voltage law. What's the first loop? The first loop is the one on the, what do you call this? The one on the left. Forget this portion for the meantime. So this is a loop, right? Forget that one first. The first loop I'm talking here is actually this loop here. Okay? You apply Kirchoff's voltage law. Okay? So the voltage source will be 12. The voltage drop will be 3. There are 3 voltage drop. 1, 2, 3. Okay? But the current passing here is same as this one. So actually we could simplify the calculation. Okay? So I place it here. A voltage source is actually a plus 12, right? Considering the first loop. This is plus. The voltage drop across this one here and this one will be the current passing through to them, okay, through them, multiplied by the resistances. And there are actually two resistances. I total, same current. So the voltage drop across this and this will be the total current times the sum of 1 plus 5. So this is 1 times 5. Okay? And the voltage drop across the 3 ohm load will be the current passing through it times its resistance. The current passing through the 3 ohm load as per our designation is I sub 1 multiplied by 3. Okay? And this should be equal to 0. This is actually our Kirchoff's voltage law. Okay? The summation of the voltages on any loop should be equal to 0. A plus voltage will be a voltage source and a negative voltage will be a voltage drop. So this is a voltage source, a voltage drop, a voltage drop. Solving for I total. There are only two unknowns here on the, okay? Solving for I total will be 12. We transpose this to, we maintain this one, minus 3, I sub 1. This one, we place it on the right. Okay, so if we try to compute for I total, there is an over 6 over here. Okay, because 1 plus 5 is 6 times I total. So if we compute for I total, it will be 12 minus 3 I sub 1 over 6. And we call that equation number 2. Okay, that's considering the first loop. Let's try to consider the second loop. The second loop is actually this loop here. This loop. Okay, the bigger one. So there is one voltage source. There is a drop here. There is a drop here. There is a drop also here. There's a drop and there's a drop. Considering the second loop, 3 is not included, right? Because the what they call this, the way will be something like this, right? We consider the second loop. So considering the voltage source, that's plus 12. Okay. The current passing here and here is same as I total. So I place it here, I total times the sum of these, 1 plus 5. And the voltage drop across this one here, plus this one, plus this one, the current passing through them is I sub 2. It's common, right? So the current, unknown current I sub 2 times, okay, there are 3 resistances in which this I sub 2 passes. It will be the 2 ohm, 4 ohm, and 6 ohm. So this is multiplied by the quantity 2 plus 4 plus 6, and this should be equal to 0. Right? The unknown in here is actually I total and I sub 2. Again, we will compute for I sub 2. I total should be equal to 12 minus this is 12 I sub 2. 1 plus 6, 1 plus 5 is 6. So if we try to compute for I total, it will be 12 minus 12 I sub 2 over 6. And this will be equation number 3. The unknown here is I total in I sub 2. On the second one, it is I total in I sub 1. Okay? But this I total is same as this one. I am thinking of something I will try to eliminate already. Okay, to formulate the next equation which we need to compute for the current passing through the 3 ohm load, we will equate, this is now algebra. Okay, that's why higher subjects are actually the prerequisite is algebra. We will equate equation number 1 and number 2. Equation number 1 is I1 plus I sub 2. Equation number 2, the right hand side is 12 minus 3 I sub 1 over 6. If we try to simplify this one, we will be having an equation involving only I sub 1 and I sub 2. And this is the fourth equation. We needed this one in the computation of the final answer. And as you could see it, the resulting equation number 4, the only unknown is I sub 1 and I sub 2. So to compute for I sub 1 or I sub 2, we must have to bring out again another formula involving I sub 1 and I sub 2. And to do that, we will equate again equation number 1 and number 3. Okay? Equation number 1, same, I1 plus I sub 2. Equation number 3 is actually 12 minus 12 I sub 2 over 6. Again, if we try to simplify this one, the resulting equation will be 6 I sub 1 plus 18 I sub 2 equal to 12. So this is actually the second equation which we haven't used yet. Okay? Okay, we call this fifth equation, and the only unknown is I sub 1 and I sub 2. And actually, to simplify the calculation, I sub 1 is actually the current passing through the 3 ohm load. And we are now given two simultaneous equations involving I sub 1 and I sub 2. Okay? We don't have to compute for I sub 2. We'll go directly for the value of I sub 1. We are given two equations. Right? So I rewrite equation number 4 it is this. And by using determinants, okay, if we try to compute for I sub 1, okay, the coefficient that will be coming here will be the right hand side, 12 and 12. So if we try to compute for I sub 1, it will be the determinant of I sub 1 over the determinant of I. This is same as x under the determinant. It will be the determinant of x over the determinant d. For the meantime, this is just I. This is I and this is I. Same, the one we use in algebra. Okay? So if we try to compute for I sub 1, okay, this portion here, we will be replaced that by the coefficient on the right hand side. So the determinant of I sub 1 will be, we will compute for I sub 1, right? And we will replace this column here by 12 and 12. So this will be, the matrix that will come out will be 12 and 12. We maintain 18 and 6, 18 and 6. And by using determinants, if we try to simplify this matrix, it should be the product of the downward minus the product of upward. Downward is plus minus the product of the upward. So this is 12 times 6 will be 72. and the upward is actually the product of 12 times 18. This is plus and a plus, but the operation is subtraction. So if we try to compute for the determinant of I sub 1, it is negative 144. Okay? And the determinant I, it will just be simply, you cover this one, take the coefficient of the left-hand side, 6 and 9, and 18 and 6. So this is 6 and 9, 18 and 6. Right? Downward minus upward. So downward is 6 times 6 will be 36. This is plus and plus, the operation is subtraction, right? Minus, this is 9 times 18. And what will come out will be negative 126. Okay? We will go directly for the value of I sub 1. We must not have to compute for I sub 2 because we are only interested on the value of I sub 1, and that I sub 1 is actually the current passing through the 3 ohm load. The problem is asking for the current passing through the 3 ohm load. So by using determinants like what I said, we computed I sub 1x and I already, so it will just be simply negative 144 or negative 126, negative, this is plus, and the value of the current passing through the 3 ohm load is 1.144 amperes. Actually, I checked this one already by using the ordinary total resistance method. By using the total resistance method, I simplify this portion here. Okay, they are in series, and the single equivalent is in parallel with this. I could take the single equivalent of this one again by taking the array parallel, right? It will be the product all over the sum. I didn't show you anymore, but I got it on my paper. Okay, and the single equivalent of this one will be in series with this 1 ohm here and this 5 ohms. Then after that, we could I computed. I just give you the summary. Our total will be 8.4 ohms. So if we try to compute for the total current emanating from the 12 volt source, it will be 1.428 amperes. It will be 12 volts divided by this. Okay? And to compute for the current passing here, okay, we will be subtracting the voltage drop here minus the voltage drop here to that 12 volt, and that will be the voltage across the 3 ohm load. As per my computation on my notes, the voltage across the 3 ohm load is 3.432. Okay, we know already the voltage over here. By using the total resistance method, we are just checking our answer, right? And if we try to compute for the current, voltage is equal to IR, right? So current will be equal to voltage over R. It will be 3.432 over 3. The total current passing through the 3 ohm load, as you check to the Kirchoff's current and voltage law solution, what comes out is 1.144 amperes. That is by using the so-called total resistance method. Okay, that's it, guys. Our solution here is an advanced thing. It's the so-called Kirchoff's current and voltage law. That is in the so-called computation of the current to any part of a given circuit, considering for the meantime 1 voltage source. Okay, that's it, guys. This is Professor David J. Los Reyes. This is from Los Angeles. Good evening.